Might take a couple of minutes longer than that, but I'll try to be quick. This thing is not working. Anyway, so when the title says mantle convection, I'm actually going to be talking about the convection and the tectonics, so the combined sort of lithosphere mantle system. Yeah, I don't know. Oh, it's over here. So how do we get rid of that? Does this work? Oh yeah, no, it works. I think that's fine now. Yes, mantle lithosphere system, and of course it. We're looking long term, so how a planet evolves over billions of years, sort of powered by some combination of the cooling of the mantle and the core and radioactivity. So when I say the influence of phase transitions, that includes solid melt phase transition. Now Stefan talked about this. He was going from like 100% solid to 100% melt. I'll just be talking about partial melting, which produces crust, which has various effects. And then also solid-solid phase transitions. And now the basalt-eclogite transition has quite a lot of effect on the tectonics of planets where the basalt is thick enough. But I'll skip that in the interest of time and just talk about the transition zone and the post-perovskite layer, which is particularly important for planets that are larger than Earth. Yeah, in fact, this workshop is on high-pressure mineral physics, but most people are focused on the Earth. I'll talk about other planets as well, including the billions and billions of planets around other stars that are expected to exist in our galaxy, although not each one individually, just as a general sense. And a general theme is that the dependence of phase transitions and mineralogy on composition is very important in planetary dynamics. Now, particularly when you get to, in general, mantle convection and plate tectonics are linked to the atmosphere and the hydrosphere through outgassing and ingassing and maybe life as well. And people who look at these exoplanets are particularly interested in this. And also mantle convection controls the heat flux coming from the core, which determines geomagnetism. So we like to model sort of the mantle convection plate or tectonic system and then parameterize these couplings with the other spheres. So let's start off with the solid melt transition, particularly the influence of partial melting. And now the key thing here is that when you partially melt a rock, the melt has a different composition than the solid. So particularly with small amounts of melt, it tends to have more silica. Of course, if you melt it 100%, it has the same composition. But yes, so you compositionally differentiate your planet, and up to about 20% or 30%, you produce basalt. And yes, you find basalt everywhere, on the Earth, on Mars, on Venus, and in my simulation code. Now, how we produce basalt? Well, this is the typical mantle solidus versus depth. This is depth for the Earth's mantle. Pressure range, this is temperature. And a typical geotherm might be roughly adiabatic, away from the thermal boundary layers at the top and the bottom. And even the average temperature can sometimes meet the solidus at a certain depth, which can generate some partial melt, which then may migrate upwards and erupt or intrude. So this is what happens in the model. So if you're ignoring this is melting-induced crustal production, then you have a purely thermal convection model. If you include this, then you can maybe erupt the melt and produce a basaltic crust. And we have shown, particularly Diogo, that this has some important effects. Now, so what happens is that the basalt is produced at the surface. This is red stuff is basalt, but then with time it can be subducted, or it can be delaminated, or different things, and it can accumulate at the bottom, and some may also accumulate in the transition zone. And yeah, Diogo showed that this can actually help plate tectonics. So at the top is a purely thermal convection model, and it goes 4.5 billion years without any subduction. But when including this magmatism and crustal production, you do actually get episodic subduction. So because the crust has a different density, it produces stresses which can help locally to reach the yield stress and generate subduction. Now, so this is a regime diagram that Diogo came up with. So without this crustal production, at low yield stress, you have mobile, that's like plate tectonics like. At high yield stress, you have a stagnant. So the yield stress is the stress at which the rock sort of breaks. And in between, well, early mobility. Now, including the melting and crustal production, the mobile lid now extends to higher yield stress. So that means it's easier to have a mobile lid regime, in a model or a model planet where you're including the production of basaltic crust. Now, this can also be an important heat transport mechanism. Let's look at a few models that we've published, this by Nakagawa and myself. So this is a model that's tracking the evolution of the Earth, including starting from a hot start with decaying heat-producing elements, and including this melting and crustal production. And if we look at the temperature versus time, if you don't include melting, then the temperature increases more or less smoothly throughout the evolution. If you do include melting, then there's a very rapid early temperature drop, and then a gradual decline. And this early rapid temperature drop is due to extensive magmatism, which removes heat from the mantle, basically, and to the surface where it radiates to space. And we can point to similar models for Mars. Well, Mars, in fact, does not have plate tectonics, but anyway, with no melting, the high radioactivity early on actually heats up the mantle, but when you include melting, there's this sort of heat pipe mode that loses heat from the interior and acts as a thermostat. So it's also been called the thermostat effect, which keeps the interior temperature more or less constant. And similar with Venus models published here. So with not including this, the temperature increases due to high radioactivity, and with this thermostat heat pipe effect, the temperature stays more or less constant with time. Now, just to consider Venus a bit more, this is a model in which there's no subduction at any time. It's a stagnant lid for the whole evolution. And when you plot the heat loss versus time, total heat loss is in red, and magmatic heat loss is in this color. And you see that they're more or less equal. So for most of the history, like virtually all of the heat loss is through magmatism. And very little is actually being conducted across the stagnant lid. Only towards the end does conduction become more important. Now, this then results in a very high resurfacing rate. If basically all of the radiogenic heat is removed by magmatism, you need a high resurfacing rate. And that doesn't really match observations of Venus, where there has been very little resurfacing for the past, say, 500 million years. So, we don't like this model very much. Here's another model. Now, this here you can actually see, how one of these simulations evolves. In this one, you do get subduction, obviously. It's a little bit episodic. This is the temperature. This is the composition, with red being basalt. And these other things are, this is viscosity, this is melt fraction, but it's best just to focus on what's happening up here. So early on, we're getting episodic subduction, and later on, it becomes a bit smoother. Now, this is a model in which the partial melt that's produced in the asthenosphere all erupts at the surface to produce crust. And now, I think we're getting a sort of continuous subduction happening around here. Anyway, so there it was sort of very episodic to begin with, and then became smoother. So another thing that can happen to melt that's produced in the asthenosphere is that it could intrude into the lithosphere or crust. And there's a diagram showing that. And that's expected to have a different effect, because now it deposits its heat, which is including both the fact that it's hotter and the latent heat, into the crust, and warms up the crust and makes it weak. So we expect this to sort of weaken the lithosphere, and it does. So here's another model in which 90% of the magma is intruded, and now, even from the beginning, you get a very sort of smooth evolution. Well, there are lots of drips. This is not proper subduction. It's sort of dripping of the crust. It becomes quite thick because there's lots of magmatism, and bits of it drop off. With time, this will become smoother. So this is a possible, scenario for the Earth. Started off with sort of dripping, and then ended up with smoother subduction, which will appear. This is the time in billions of years. Fortunately, it's faster than real time, but it still takes a while to get through the movie. And we should soon begin to see the appearance of somewhat longer-lived subduction zones instead of these pulses. Just be patient. Don't think too much of beer and caipirinha. Yeah, now here is sort of some sort of long-lived stuff going on. Yeah, well, they're sort of building up. I mean, they're high viscosity, and we're getting a sort of region of high viscosity in the middle of the mantle. Yes, now we're getting things that last a bit longer and are more coherent. Red is basalt, yes. So here it's really building up into a thick layer at the bottom. Yeah, more about that shortly. Anyway, Diogo came up with this regime diagram for the tectonic behavior as a function of the extrusion rate. So this is purely intrusive, this is purely extrusive, and found that there's this new regime where most of the magmatism is intrusive, and it's called this plutonic squishy lid. You saw it, with all the dripping and so on. And that this regime doesn't depend on yielding. So actually it exists for the whole range of yield stress. Now, Antoine Rosel is great at drawing. He's a sort of artist. He comes up with these nice artworks of how things are working. And this is how this mode works. So it weakens the lithosphere in places, not everywhere. This is where the upwellings are. And then regions of the lithosphere are able to move horizontally short distances. Now this sort of ties in with high-resolution regional models that various people have run, including Taras and his co-workers. This is Sizova, Taras, Guerrier, and some others, in which, and this is actually one of Boris's former students' models, in which there's a lot of magmatism, of intrusion, very sort of weak crust and lithosphere. So at least, having these high-resolution models displaying somewhat similar behavior gives confidence that the global models are sort of okay. That was for the early Earth, those models. It's also been interpreted as being applicable to Venus. So there's this, we didn't write this, these are people who know about Venus. And they also think that this squishy lid regime is applicable to Venus's inferred geological history. So we can summarize some different tectonic modes. These are the traditional ones: mobile lid, which is like plate tectonics, or stagnant lid, where the lithosphere is not doing much. And sort of episodic lid is where it's mostly stagnant, but you get these episodic overturns. But now there are these new modes which are related to magmatism. So there's the heat pipe. Well, this has been talked about for some time. That's where, the magmatism is extrusive and transports a lot of heat from the interior. And the platonic squishy lid, this is new, where the intrusion is weakening the lithosphere and causing it to be deformable. So now let's move down to the transition zone. And we've seen this type of diagram before. This shows the mineralogy as a function of depth, right? But we've usually seen it plotted for the average mantle composition of pyrrolite. So here we show basalt and Harzbergite as well. And what you see, well, in terms of the transition zone, people have written a lot of papers about the influence of these olivine phase transitions to wadleyite and then ringwoodite, and particularly the ringwoodite to bridgmanite and ferropericlase at 660, which is endothermic and can cause partial layering. But when we look at basalt, we find that the garnet, which dominates the basalt, actually undergoes the transition to the lower mantle assemblage, including bridgmanite, calcium perovskite, which is known as Dave Mauite, which we've heard about, stishovite, and so on. Anyway, at a greater depth. So there's this region between about 660 and about 720 or so kilometers, in which the pyrrolite or Harzbergite component has converted to the denser phase, but the basalt has not. And when you calculate density maps using software such as Perplex, you see that this is now basalt or morb minus Harzbergite, so it's the density difference between either Harzbergite or pyrrolite as a function of depth and temperature, and you see that it's actually negative in this depth range. So normally the basalt mineral assemblage is denser than either pyrrolite or Harzbergite, but in this depth range of several tens of kilometers, it's less dense than the other compositions. And so this means that basalt can get stuck in this depth range. So we can see here that you tend to get morb trapped in the transition zone, at the bottom of the transition zone, and by the same mechanism, Harzbergite can also get trapped sort of at the top of the lower mantle. And this has been seen in various simulations that have been published over the years. Ogawa was one of the first to publish these thermochemical models that included this type of differentiation, and then our models in the early 2000s. Jeff Davies modeled this and called it the basalt barrier. So that's a nice name, the basalt barrier, and then there's been some other models as well. So basically anyone who makes a serious attempt to include compositional differentiation in their models and model mantle convection, finds that this to be an important effect. And we can see it here in this paper, that basalt is building up in the transition zone. Now, for an Earth-like model, this is not a big enough effect to prevent slabs from going through. So you can see, well, slabs, going through typically in Earth-like models. But in a Venus-like model, in which you don't have subduction, at least not today, this is such a large effect that it can basically layer the mantle flow for periods of time and cause intermittent breakthrough. So this was a paper that we published, in fact, last year, 2023, yes. What's happening is that for long periods of time, the flow between the upper and lower mantles is inhibited due to this basalt barrier effect. Now, it has a larger effect on a sort of stagnant lid planet because the temperature variations in the interior are smaller. And what matters here is the ratio of thermally induced density variations to compositionally induced density variations. On Earth, that's pretty large because the slabs have an anomaly of 1,000 Kelvin or something. But on a stagnant lid planet, the upwellings and downwellings may only have anomalies of a couple of hundred Kelvin. So much lower. And you see a strong buildup of basalt and sort of partial layering, which occasionally overturns. Now, if we look at the nice movie that's coming up, this is temperature, this is temperature, this is composition. So to begin with, there's no layering, and you get whole mantle convection. But then, over time, the crust forms, and it's stagnant lid, so there's no subduction, but you get sort of delamination of the bottom of the crust, and you see it is building up, in the transition zone, and some also makes it to the bottom. So with time, you build up this layering, and then you just saw an overturn event. Now this is purely an internal overturn event in this simulation. So the lithosphere stays there, and you get this internal overturn, which does cause widespread volcanic resurfacing, because you have all this, see the lower mantle becomes hot, the upper mantle is cold, but when the layering breaks down, this hot lower mantle goes into the upper mantle and causes widespread melting, which then resurfaces the planet. So this is an example of how you can resurface a planet like Venus without any subduction or lithospheric overturn. You just have an internal sort of overturn that causes widespread volcanism. Now, another feature of this study was that we realized that basalt is not made of olivine. Now, you sometimes can have olivine in basalt, but it's not one of the major minerals. But people who do global mantle convection models typically assume the same rheology for all substances, whereas people who model the crust, or lithosphere, like Boris and Taras-Gurya, are typically assuming that each material has a different rheology, often based on laboratory experiments. So here we also chose a laboratory-based rheology for our basalt. It's not the same as the other materials, and can have some important effects as well. Now, this is a different type of overturn that the model displays. This is actually a lithospheric overturn. So here, subduction starts somewhere, and then it spreads around the planet, and you get a global lithosphere overturn. So depending on the assumptions, we can generate either with this type of model. And here's a nice movie that shows this. So again, it takes a while for things to build up. So basically, the main difference between this one and the previous one is that the crust is less strong. The crust is weaker, and this allows actually the whole lithosphere to go down sometimes. If we wait long enough, here we go. Yeah, something happened. So yes, here's another possible, global resurfacing method, which actually involves global subduction of the lithosphere. Now, this is, people have published models where you get episodic overturn before. The main difference with this one is that in between overturns, the lithosphere is deforming because the crust is relatively weak. So we call this a deformable episodic lid. So it's not as if the lithosphere is just sitting there doing nothing between overturns. It's actually can be deforming. And that's actually what you observe on the surface of Venus. It's, people are inferring that the lithosphere is deforming. Anyway, combining these new modes with modes that you knew about before, there are actually quite a few possibilities for the tectonics of Venus. There's the stagnant episodic volcanic resurfacing, which I showed you. That's where the lithosphere doesn't actually subduct ever, but you get these bursts of volcanism from time to time. There's the deformable episodic lid, where you can have deformation all the time, but then you get these bursts of global subduction. You can have the plutonic squishy lid, which can also be episodic, actually, anyway. Or we can have the conventional stagnant overturn, yes, or stagnant lid heat pipe, which I was saying doesn't match observations. Okay, well, that was talking about the surface and also the transition zone. Looking to the bottom, we can also couple these models with core evolution. Now, because the mantle basically controls the heat flow from the core, various people have come up with parameterized core models, and we can include those. And the core cools with time. Now, Takashi Nakagawa and I have published a number of papers on this, and I won't go through them all. I'll just show one picture, which shows the influence of tectonic mode. So actually, these are each column is a different simulation with a different friction coefficient. Now, this is really low, which means that it's plate-like behavior the whole time. On the right, it's stagnant lid behavior the whole time, and in the middle, you have episodic overturn. One thing you notice is that the episodic cases build up a thicker basalt layer at the bottom than the continuously mobile cases or the stagnant lid case. But this shows the influence on core evolution. So this is the core mantle boundary temperature versus time for the different cases, and this is the inner core size versus time. So the inner core is not there for most of the evolution, as we've heard someone talk about before, but then it may nucleate, in this case about 1.5 billion years in the past, and grow. And it's interesting that, yes, for these simulations, the plate tectonic-like case and the stagnant lid case actually have a similar cooling history. And that's interesting, because usually people say, well, a stagnant lid planet must have slower core cooling because there are no slabs to absorb the heat. But in this case, it's actually very similar. And the case that's slower is the one where you're dumping lots of basalt on the core mantle boundary, which acts as a blanket to slow things down. Anyway, let's talk about calculating these density contrasts. Most of the cases I've shown already are using some sort of assumed density profile versus depth for the basalt and the Harzbergite components. You can also calculate these using one of the free energy minimization packages, and we've heard about Perplex and Hefesto by Stixrud and MageMin, which Boris talked about. And they should all, and it has been tested actually, that they give the same result for the same thermodynamic database. So it doesn't matter which one you use, it should give the same result for the same database. But the key point is that different thermodynamic databases may give different predictions, and even updated versions of the same thermodynamic database, such as subsequent versions of the Stixrud and Lithgow-Bertoloni database. And I'll just show an example of that. So there is a tendency for people to use these to calculate their physical properties and then assume that it's perfect and we don't need to worry about uncertainties or something. But I say that's not the case. Now this is just reminding you of what we've seen already. So there are phase transitions here, and also the phase transition to post-perovskite. So here it's shown at this depth for bridgemanite and a slightly shallower depth for bridgemanite when you have basalt. And yes, simulations, these actually are using densities calculated using the 2011 database, and in this case, subducted basalt settles above the core mantle boundary. And we're used to seeing this type of thing in simulations dating back to sort of Christensen and Hoffman, 1994. But when you calculate the same thing using their 2021 database, you find that basalt does not settle above the core mantle boundary. And the reason is, we can infer by looking at these density profiles. So in the earlier database, yeah, the density profiles for morb and pyrrolite stay more or less parallel through the post-perovskite transition. But in the 2021 database, while pyrrolite undergoes the post-perovskite transition, morb basically stays the same. So for some reason, the post-perovskite transition is suppressed in the morb assemblage in the 2021 database. And that doesn't seem to match some papers that have been published. And no doubt Renato would have something to say about that as well. But anyway, it's something that you have to, worry about. Another difference here, okay, in the earlier database, and for this, these are two different published basalt compositions. So for this basalt composition, there was basically no basalt barrier layering in the earlier database, but there is in the 2021 database. So yes, you have to worry about uncertainties in the thermodynamic database, and maybe compare to published laboratory papers to check whether they're predicting something reasonable. Anyway, in the last little section, I talk about planets that have a lot of post-perovskite, these so-called super-Earths or super-Venuses. And this has been a real growth industry since the first exoplanet has been discovered. It's a sort of headline news when a new potentially Earth-like exoplanet is discovered. And how many of these might we expect? Well, firstly, this is the sort of estimate that some people made, these people made, that 20% of Sun-like stars have a roughly Earth-sized planet in the habitable zone. Of course, it's very debatable, but if that were correct, then there would be 40 billion potentially habitable Earth-like planets in our galaxy, of which 2,000 within 60 light years of Earth. So that's a lot, and some of them have been discovered. So this is sort of out of date, but still the distribution looks the same. About 6,000 exoplanets of all types have been discovered. And this is a standard sort of diagram which shows them on versus orbital period, which maps into distance from the star. And this is size relative to Earth. So here's one Earth and sort of Neptune size or Jupiter size. So yeah, a number of Earth-sized planets or smaller have been discovered. And they're sort of classified into the hot Jupiters are ones that are close to the star, cold gas giants like the actual Jupiter, ocean worlds, sort of with 4 Earth radii, and then rocky planets, and the lava worlds are the rocky planets that are so close to their stars that they're partially molten. So now the largest, these are potentially habitable ones. Well, so a number have been discovered. And so we and other people are interested in predicting their dynamics. Of course, there's not much data. But astronomers are planning to obtain spectra, or they already have obtained spectra for some of the atmosphere. Anyway, so what about these planets? Now, many of them are larger than Earth. The largest sort of rocky planet that one can imagine has about 10 Earth masses. If it's larger than that, then it accumulates a lot of gas and becomes a gas giant. And so these are the pressures in Earth's interior. For the largest super-Earths, the mantle, or generally, you multiply by the relative mass of the planet. So super-Earth will go up to about 1.4 terapascals in its mantle. And the effects of this are that you might get additional phase transitions, so-called post-perovskite, and so on. There'd be a large influence on viscosity, a large probably increase in thermal conductivity, decrease in thermal expansivity, and so on. So this has led some people to think that the deep interiors of these large planets might be sort of stagnant. Anyway, here's one of these nice images showing the perovskite structure and the post-perovskite structure. So you can see that the post-perovskite structure is sort of layered, and that actually makes it anisotropic. So the viscosity for deformation is different along one direction than another. Now, Philippe nicely talked about diffusion creep and dislocation creep. Amann, Broadholt, and Dobson actually calculated using density functional theory, the activation enthalpy as a function of pressure for actually both MgO and for perovskite, and up to 1.4 terapascals. And this is their result. So this is the, you often hear about activation energy and activation volume. This is sort of combining them, so it's total activation enthalpy versus pressure. So again, the bottom of Earth's mantle is about here. We're going up to much higher pressure. And yes, the problem is then that it's anisotropic. So diffusion in one direction is different from diffusion in perpendicular direction, and we're not quite sure which is a sort of average to use. So anyway, we can make predictions using both of these for just simple diffusion creep. This would be the viscosity profile for the easiest diffusion. So you get a probably decrease and then quite a large increase along an adiabat. This is along an adiabat. For the most difficult diffusion direction, you just get a really high viscosity. But that doesn't seem to be what we're seeing in Earth anyway. So there are indications that the viscosity might decrease as you go into post-perovskite. And other material properties I won't go into, but they also change like this. So we can run models, of course, which are similar to the previous models, except for bigger planets. And the net result, so these are planets going up to 10 Earth masses. For these cases, there's no melting switched on. But what happens then is that the larger planets tend to have pretty hot interiors. That's because this is for the higher viscosity, and this is for the lower viscosity limit. But what happens then is that, whereas along an adiabat, it's predicted that the viscosity should increase a lot, what happens is that the temperature profile is not adiabatic. There's some sort of self-regulation, and this occurs, well, if you have internal heating, basically, that the temperature will self-regulate to what it needs to be to get rid of the heat that's input. So, and that turns out to be a super adiabatic temperature profile, leading to a roughly constant viscosity. Okay, well, that was assuming diffusion creep, whereas, as Philippe was saying, dislocation creep might be more important. Now, at the same time, Shun Karato made a different prediction about the viscosity of these super-Earths. He predicted that you would transition to a different diffusion mechanism, which is this interstitial diffusion. Somehow atoms, stuck into the in between the other atoms, and that would predict, according to him, an actual decrease in viscosity with increasing pressure. So, okay, we can model all of these possibilities, remaining sort of agnostic as to which one might be most accurate. So this is the sort of Karato-like one, lower bound, upper bound, and also we can have a composite rheology that's including dislocation creep. And here's a model with composite rheology, 10 Earth masses, including magmatism. And what we see is that the whole thing is convecting. This is actually a passive tracer that can outgas when you erupt. So here's basalt. Anyway, so the whole planet is active, and particularly this composite rheology helps it, because where you would otherwise get very high viscosities and high stresses, when you have dislocation creep, that it tends to become active there. So anyway, we predict that these large planets are still sort of actively convecting, regardless of what the rheology is. And this just shows some outgassing or eruption actually versus time. So they all produce basalt for billions of years, which is opposite to some previous predictions. Another interesting thing I can point out is that the larger planets tend to be more susceptible to compositional layering. And that's, again, for what I talked about before, it's related to the ratio of thermal buoyancy to compositional buoyancy. At high pressure, the thermal expansion coefficient tends to become very low. So thermal buoyancy is quite low. On the other hand, the compositional density difference probably remains more or less the same. So that means that compositional density variations become more important, and you can end up with sort of large-scale compositional stratification of these planets. And this is not including any early sort of magma ocean type effects. It's just layering that builds up due to melting and crustal production. Yes, internal heating has a big effect. I mean, people have talked about the sort of cosmic abundance of these heat-producing elements versus time, people like Steve Moses. And so planets that were formed at different times might have different abundances of heat-producing elements, which, of course, greatly influences their activity versus time. So I'll just say one more thing about other planets and then wrap up. The models I showed so far don't include any post-perovskite transitions. And sort of Renato will probably say that's not correct. And actually, here's a diagram from Umimoto et al. Paper, which shows possible transitions beyond post-perovskite at very high pressures. So, but we don't know, at least I don't know the physical properties of these phases, so it's difficult to put them into a convection model. So mineral physicists, please calculate these. And another thing is that exoplanets can have different compositions to Earth. So there's a tendency to, just scale Earth up. But, based on, so Rob Spargaran, who was a student at, in my group, working mainly with Maxime Borma, sort of quantified this. So looking at the stellar abundances of the planet-forming elements, you can then go through a process similar to what Bill was talking about. You have to account for the volatility to then infer the planetary abundances of the planet-forming elements. And then you can come up with different possible planetary compositions. There's this table of 21 sort of sample compositions that Rob came up with. And then you can use Perplex or equivalent to calculate the mineralogy of the mantles. So you can see it varies quite a lot. So this one, I think, is Earth, yes. This one is with higher magnesium over silicon, so now there's no ferropericlase. This is with high magnesium over silicon, so now there's more ferropericlase, which actually reaches the surface according to the Stixroot database. That's probably not correct, anyway. And yes, with high minor, which means calcium and aluminium, you get more of the nice stuff which makes basalt. So clinopyroxene and garnet. And you can also see that if you calculate melting of these, you're going to get different things. So here you would get a lot of basalt, like maybe you can get 50%. Here you get less. Yeah, and so on. So this is work that Rob was doing, and I won't, well, he needs to write it up and publish it anyway. So what effect do these different compositions have? Well, of course, it changes the density and so on. Probably the viscosity, yes, which will change the sort of planetary history, the tectonics. And of course, it changes the melting. I mean, the solidus, the liquidus, the amount of basalt that you can produce. Yes, which is going to change. So more work needs to be done on this. So to wrap everything up, composition-dependent phase transitions make a big difference to planetary dynamics. In fact, I think more than the sort of classical phase transitions in a pyrolytic composition. Igneous extrusion and intrusion influence the tectonic mode. subductive basalt causes partial mantle layering, both at the transition zone and above the core mantle boundary, and that influences the core evolution. And things for the mineral physicists to calculate would be maybe to check exactly when the post-perovskite transition occurs in basalt, referring to the latest Stixrud database, and check the rheology of post-perovskite and other physical properties, and check the melting of these exotic planetary compositions. Right, thank you.
Thank you, Paul. So we have a few questions.
We can also discuss over beer later.
Paul, what about the initial conditions on these models? I mean, they all start off convecting vigorously, so you've put in I've seen a lot of people who do these planet building models from the accretion of the super Earths, and they start off extremely stably stratified and take billions of years to develop a super adiabatic gradient. What do you think of that?
Okay, well, I'm not aware of those models. I mean, usually, based on simple scaling arguments, you expect the larger planets to start off hotter than the smaller planets, which would tend to.
The gradient. Not the temperature, the gradient.
Well, but they when you have large impacts, and they should have large impacts in the later stages of accretion. Hmm? No, they can heat the whole planet, including the core.
No, but the majority of heat is dissipated within a few radians of the size of the impact.
Oh, it depends on the impact. I'm talking about giant impacts, yeah.
What if there's no giant impacts?
Well, there should be.
Well, there's not always. Venus didn't have that.
No, I mean, we have a couple of papers now about giant impacts on Venus. They just didn't form a moon. But, the standard solar system accretion models do predict giant impacts in the late stages of planetary accretion. Just they have a low probability of forming satellites.
The more giant the planet is, the more giant the impact has to be.
Exactly.
So does that really work? Let's scale up. Why not? I don't know.
Yeah, no, I haven't seen actually these sort of accretion models for solar systems that produce super Earths. Maybe they exist. But.
It's in the literature.
Paul, that was fun. I have a couple of comments. First comment, NASA just reported recently, about 3 weeks ago, that some astronomers have imaged crystalline olivine and crystalline pyroxene coming out of the middle, that is the star area of accretion disks, moving to the outer areas of the limb. This is a very important advancement because it really has actually added evidence to some of the models that we have for what is happening in the protoplanetary disk. So we're seeing live crystallization happening in the protoplanetary disk. Now, what can you do with that? Well, I would encourage you to sort of, when looking at your compositional variation, looking at compositions that go from pure pyroxene, low calcium pyroxene, MgSiO3, all the way up to perhaps even pure olivine, Mg2SiO3. Next comment would be, I saw a lot of basalts in some of your models, and I think I felt very uncomfortable after a while. You can actually limit how much, and we were talking about this earlier this week, you can limit how much basalt can be produced in Earth, in all your other models, by essentially something like aluminum. Granite and basalt both basically have 16 weight % Al2O3. In the mantle, at least in compositional models, one I like, has approximately, say, 4 weight % Al2O3. So once you run out of Al2O3, you can't make any more basalt. So that's sort of a mass balance in that system. But I was seeing like 20, 35% basalt in those models, and I was wondering,
well, when
looks like too much after a while.
Well, when you do a melting experiment, starting with pyrrolite or something, you can produce about 20% basalt. And that's what Sticks
I'm-
Root
I'm-
also
No, that's
publishes.
okay, but I was just
Yeah.
talking relative to the entire mass of the mantle. So the mass of the mantle, how much, clearly, let's go to the extreme. You cannot have 50% basalt and the remainder peridotite.
Right.
That's what I'm talking about,
Yeah.
trying to do a mass balance that way. Now I have a question. When geochemists, like myself included, start thinking about mantle convection and the composition we see in basalts, and this is more particularly about trace elements, we'll often in our minds think about short circuit circulation systems, such as the upper mantle or the source region for mid-ocean ridge basalt has turned over 10 times. Oh, sorry, has turned over 10 times, and less likely you've had larger circulation convection patterns. Is that a good way to think about it, or should I not have that idea? That is, there's a lot more overturning of the mantle in the top 600 kilometers than overturning of the whole mantle.
Well, well, there might be in the sense of a small-scale convection sort of below the lithosphere, but if you're talking about subduction of the lithosphere that contains the basaltic crust, that typically seems to go through into the lower mantle, according to seismic tomography models. So I think the sort of basalt cycle might go to the deep mantle, whereas you can still have small-scale convection that's.
Some people actually think that the mantle transition zone has some basalt and it's actually just going around quicker. I don't know.
Right. Well, as I was saying, the mantle transition zone is probably basalt enriched, but yeah, that's not basalt that immediately peels off from the slab as it goes through. At least I don't think so. Some people have argued that it might be, but generally the basalt seems to be carried down by the slab into the deep mantle, and then it can sort of separate at the core mantle boundary or something, and you get blobs of basalt coming up that can later settle in the transition zone.
So I have a couple of questions or comments. I mean, it's kind of, blurry. I mean, at the very beginning, I think the second slide, you showed your temperature profile. I mean, that was from Diogo's calculation. And so the temperature at the bottom is very low. I mean, much lower than the present day estimated temperature at the CMB. And of course, if you were to increase that temperature to something more realistic, you would have much more melting than what you would want. So that kind of, for me, I mean, it means that, of course, you're trying to get as realistic as possible, but it seems that there's something missing there. I mean, so what's going on? I mean, why do you have that?
Well, the core, depending on which model. Anyway, we're normally starting off with a hot core, like 5,000 Kelvin or something, and then but by the end, it typically cools more than the Earth's core is inferred to have cooled.
Right, exactly. So that's my point, I guess. I mean, if you were just to take that, you would predict much more melting than we have at present day, right? So there's probably something problematic about that. I don't know how to solve that problem.
Yeah, well, you need something that slows down the core cooling, such as a basal magma ocean.
Right.
Maybe.
And I guess my second point or question was about the super Earth. And I mean, in the recent work we've done on compressible convection, we find that, I mean, we have this equation of state, which may not be, I mean, it's quite simple. But what you find is that when we increase the dissipation numbers, therefore the compressibility, what happens is that we don't increase so much the temperature gradient at depth because alpha decreases with pressure. So in fact, what you do when you do that, you increase the curvature of the isentropic temperature profile, which means that at some point you may end up having a stratification at the top just because what is transported along this temperature gradient, the isentropic temperature gradient, is actually much bigger than heat production from radioactivity or anything like that. So you could actually have stagnant lead even without composition, without effect of viscosity. So you can have the upper part that becomes stagnant, and you start to have convection below that. There was a paper by Yannick Ricard and Thierry Alboussière on that. I also did some calculations like that. And so I was wondering, I mean, in your case, I don't know, I mean, your adiabats, So what's the dissipation number for that, and what's, I mean, typically, do you know that? Or?
Well, it's not so high because, yeah, as you say, expansivity decreases, so the adiabatic gradient becomes shallower.
Right.
So yeah, we don't calculate very high dissipation numbers for these large planets for that reason, it seems.
Okay.
And they become less compressible as you go to higher pressure.
Yeah. Yeah, there's a limit to that. Clearly.
Paul, yeah, I have a question regarding when you use this composite rheology equation in your simulation. Do you have a way to track later where one term of the viscosity rheology law is appears, or where is the other one which which occurs?
Yeah. One of the outputs is the sort of fraction of deformation that's due to each mechanism. So we can plot that, yeah.
But it's fraction. It's always both together.
Yes.
Okay.
But usually one dominates, greatly. Yeah.
Paul, so very interesting. So on slide 15, out of the 200 you showed, you actually
15.
looked at models where you included magmatism, and suddenly the range of mobile lit regime seems to be expanded to much bigger yield stresses, but with little patches.
Oh, yeah. Where was that?
Slide 15, I think.
Are they numbered? Oh, it's further back, wasn't it? Yeah. Yeah, well, this is probably due to some randomness, and yeah, Maxime and his students are looking at this at the moment. That you can run the same case with the same parameters, just different random perturbations, and maybe most times it'll be episodic or something, but once it might be stagnant. So what we probably need to do is run each case 10 times or something, and then take a majority vote.
All right. And a second question is, post-perovskite, as you showed, is very layered, so it's probably also viscously anisotropic.
Yes.
So what would that do?
I'm not sure. I mean, it depends whether the crystals are aligned or whether there's a sort of random with respect to each other. I'm not the expert. Maybe Philippe knows.
Well, if you do this for the lithosphere, then anisotropy has been shown to have a very important impact. Yeah, like gneiss rocks or just layered rocks or something like that. So suppose it might be something you may want to add.
Yeah, it might. Well, even on Earth, seismologists find it D double prime to be quite anisotropic, as I understand. So, it probably is anisotropic viscously as well.
Very interesting presentation, Paul. Here. For the episodic scenarios with episodic tectonism, what's controlling the period between two episodes of tectonism?
For the episodic, well, I think what happens is that if referring to the basalt barrier mechanism first, what happens is that the temperature difference between the upper and the lower mantle, builds up over time when there's negligible mass flux between them, and then at some point it reaches a critical amount at which the sort of extra buoyancy of the lower mantle, due to the fact that it's hotter, exceeds the sort of resistance to flow, and then it overturns. And as for the sort of lithospheric overturn mechanism, I think that the lithosphere tends to become thicker with time, and eventually the stress associated with its thickness exceeds the yield strength, and so it can go down.
Yeah.
The last
Thank
question.
you. Oh, thank you. Yeah, I definitely didn't follow some of the finer details, but maybe not even the big picture, but I think what you showed is a model that sort of showed subduction for a while, and then it became more and more like it is today, and you got that by starting with a solid mantle and then partially melting it and intruding the crust and the lithosphere and the crust.
Mm-hmm.
And so you started with a solid and then began melting. And then Stefan showed earlier in the week that you started with a molten mantle and then started crystallizing it. And then so he got a bunch of nice LLSVPs. You got a whole bunch of very nice subduction zones. Is there any model that can do both?
Yeah, I expect we can set my code up. I mean, Stefan was using my code as well, so we can probably set it up to do both. Maybe next time.
Okay, so let's thank you, Paul again.
Well, I think actually we should thank all of the organizers. So we should a round of applause for all the organizers. Right.
So thank you all for all the speakers that we invited for accepting the invitation, all the audience for everything. Thanks so much. I think it was a very productive week. So thank you. Thanks so much.